In this exercise, we're given this infinite sum that approximates pi over 4. We're supposed to write a function that calculates this sum until the next term in the sum is less than some given tolerance epsilon. Now, to me, the logical place to start is to do this problem by hand, see what the terms look like, examine my solution approach, and then convert that into a Matlab program via some pseudocode. So, if I'm calculating terms in this summation is, for k equals 0, I get negative 1 to the 0th over 1 times 2 times 0 plus 1, plus, when k is equal to 1, I get negative 1 to the 1st times 1 over 2 times 1 plus 1. When k is equal to 2, I get negative 1 squared over 1 times 2 plus 1, plus, when k goes to 3, negative 1 cubed over 1 times 2 times 3 plus 1, plus a bunch of other terms. These 4 terms are probably enough for me to be able to pick up the pattern on how I'm going to solve this problem. So this term, when k is equal to 0, becomes 1 over 1, which is just 1. Our next term here, when k is equal to 1, I get a negative 1 times 1 over 3, so this is minus 1/3. When k is equal to 2, I get a negative 1 squared, which is 1 over 5, so plus 1/5. Negative 1 cubed is negative 1, so I'm going to subtract a number. 1 over 2 times 3 plus 1 is 1 over 7, plus a bunch of other stuff. Now I think my next step in setting up this problem is to define some variable names. I know that I'm going to need a tolerance, so I have a tolerance, epsilon. I'm going to call that EPS. I'm also going to calculate a bunch of terms for k equals 1, k equals 2, 3, so on and so forth. So I'm going to have these terms, which are all negative 1 to the k times 1 over 2k plus 1. I think in my parlance I'll call each of those term. I'm also going to keep adding these up. When I calculate my first term, my estimate for pi over 4 is going to be 1. When I calculate the term for k equals 1, I'm going to add these two together. That's going to be 1 minus 1/3, which is 2/3. So I'm going to keep a running total as I loop through these. Since that's my estimate for pi over 4, I think I'll call that EST. Probably the next logical step, for me anyway, in the solution process is to set up a table that outlines term by term how I'd calculate my estimate. So now that I've defined my variables, I know I have to keep track of k, I have to keep track of the variable term, and I have to keep track of my estimate EST. For this term, when k is equal to 0, the term I calculate is 1. If I don't know what any of these other terms are yet, my estimate is just going to be whatever this is. So in this guy here, after I calculate each term, est is going to be my old value of estimate plus term, I think. So I want this to be 1, so this would be my old value. 0 plus 1 is equal to 1. So when k is equal to 0, my estimate for pi over 4 is 1. Then I'm going to have to add 1 to k, so when k is equal to 1, term is minus 1/3. I'll take this 1, subtract 1/3 from it, that'll be 2/3. Then I increase k, k is equal to 2, this becomes 1/5. So I take this previous value, which is the sum of these two terms, and add this term to it. So 2/3 plus 1/5 is 10/15 plus 3/15 is 13/15. And for k equals 3, I get negative 1/7. And my estimate is going to be this value, 13 over 15 minus 1 over 7, which is something that I probably don't really care about. So now let's try to take this process and cast it in terms of pseudocode. So my pseudocode is just kind of a rough outline of the steps that I went through to create this and add up all of these terms. So I like to start my pseudocode with the looping process. If the absolute value of term is greater than EPS, so once I've calculated a term, I check to see if it's bigger than my tolerance. If it is, then I need to calculate the sum and the next term. To calculate my sum, EST is equal to EST plus term. That's basically what I'm doing in this last column here. I have to increase k, and I have to calculate a term corresponding to this new k. So term is equal to -1 to the kth times 1 over 2k plus 1. And then I loop around that until this is no longer true. The order that I did these is kind of arbitrary. I can usually set my initial conditions so that it'll satisfy the order that I picked arbitrarily here. To initialize, to create this one, I set k equal to 0, I set term equal to 1, and since I'm adding this here first, I need this initial value for EST. Now let's see how this works. Is the absolute value of term greater than EPS? Well, I need to initialize an EPS as well. I'm going to arbitrarily say EPS is equal to 0.15. That should stop this process when I get to this term. 1/7 is less than 0.15. Is 1 greater than 0.15? Yes. I'll go ahead and add EST equals EST plus term. So 0 plus 1 is 1. I should get 1 here. K will be 0 plus 1, which is 1, and I'll move down to this row. The term that I calculate will be -1/3. Then I go back up here. Is 1/3 bigger than 0.15? It is, so I'm going to go ahead and add these together to get 2/3. I'm going to increase k to get 2. I'm going to calculate the term corresponding to that and keep going. This overall process looks like it's about right. Now there's nothing special about this process. I could do things a little bit differently if I like. For example, I could exchange the order of these two commands here. So I could say first, term is equal to -1 to the k times 1 over 2k plus 1, and then I could increment k. Since I'm adding 1 to k after I calculate term, and since my first term is still 1, what I'm going to have to do in this case is start out k at 1. So now when I go through this, when I start things up, the first value of term is 1. That's bigger than 0.15. I'm going to add that to that and get this. Then the first value of term I want to calculate corresponds to k equals 1. That's why I initialized k at 1. So that will calculate this value for term. Then I'll increment k to k plus 1, but then I'll make this addition after I increment this. It does things in a slightly different order, but it should have the same effect. So for the first set of pseudocode that I did, I'm going to write my Matlab code based around that, so you can forget the stuff that's in red if you want to. I'm going to use the first version of the pseudocode that we created. Now we just need to transfer that to Matlab. We have a looping structure here. Our loop termination depends on a condition. That probably means that a while loop is more natural for that particular looping structure, since the condition is built into the while loop. First, the initialization of variables is really just copying these lines over again. So I'm going to set EPS equal to 0.15. In Matlab, I'll tend to follow that with a semicolon so I don't have to see it. EST is equal to 0. Term is equal to 1. And k gets initialized to 0. Now, if I use a while loop, my syntax is while, and this is what needs to be true to continue with the while loop. I have an absolute value on term. The Matlab command to do an absolute value is ABS. So while the absolute value of term is greater than EPS, we'll do this stuff. So I'll add est plus term to get my new value of est, increment k, and then just convert this to Matlab with the appropriate operators. So term is equal to -1 to the kth value. I just multiply that by 1, so I can divide here. 2 times k plus 1. All of these values are scalars now, so it doesn't matter whether I use slash or dot slash or times or dot times. Then I end the while loop, and I'm done. Now after I've done this, I'm going to want to walk back through my example with this code to make sure that it actually works before I put it into Matlab. Because if I know what I'm supposed to get out, then it's easier to check my results. So here's my Matlab code. I'm going to go through the steps as I walk through this while loop and make sure that I get what I should get based on my previous worked example. First time through, k is equal to 0, term gets set equal to 1, est is 0, then we enter the while loop. The absolute value of term is 1, EPS is 0.15, 1 is greater than 0.15, so I enter the loop. Est is equal to est plus term. So 0 plus 1 is equal to 1, and the first value of my estimate is 1. Then k is equal to k plus 1, 0 plus 1 is 1. Term is -1 to the first, which is -1 over 2 times 1 plus 1, which is going to be -1/3. Now I hit the end statement for the while loop, go back up here. Term is -1/3. Absolute value of term is 1/3. That is greater than 0.15, so I enter the loop. Est is equal to est plus term. My old value of est is 1. Term is -1/3, so this is 2/3. Then I get to this statement, k is equal to k plus 1. 1 plus 1 is 2. -1 squared is 1 over 5, so this is plus 1/5. I hit the end statement for the while loop, go back up here. The absolute value of term is 1/5, which is 0.2. That is greater than EPS, which is 0.15. So I enter the loop. Est is its old value plus 1/5, which is again 10 over 15 plus 3 over 15, which is 13 over 15. K is equal to k plus 1, so 2 plus 1 is 3. Term is -1 cubed, which is -1 over 2 times 3 plus 1, which is -1/7. Go back up to the while statement. 1/7 is slightly less than 0.15, so this is not satisfied, and I'm done. I jump out of the while loop. There's nothing else to do. This problem is over, and my final value is going to be 13/15. Now let's go ahead and implement it in Matlab and make sure it works. Here's my script file in Matlab that implements the while loop that I set up. If I go to the command window and run the script file named ex10p9, okay, my initial value for est is 1. My first term is -0.33, so after that iteration I get 0.667. Let's see, then I get a 0.2, which is my 1/5, which results in my final estimate as being 0.8667, which is 13 over 15. My next term is -1/7. That terminates the loop. So it looks like it's working according to the example that I did previously. Now let's set this to be a higher tolerance. Let's say I want my change to be 1e to the -5. And if I'm doing that many iterations, let me not see this or this. There are my semicolons. Save. Okay, and we want to see what est is, and we want to check that compared to pi over 4. Cool, they're the same. Now that my program's working, I'm going to change it to a function. So, function. What I'm returning is est is equal to ex10p9 of EPS. I'm sending it my epsilon, and I don't need this stuff here. Now I'll save that. I can run my function at the command window. So ex10p9 of, if I make my epsilon 1 e to the minus 5, I get the same number back. It looks like I've met my program's requirements. Now there is a problem with while loops. If they don't terminate, Matlab will just go away and think about this forever. Let's see what happens if I send it an EPS of 0, so that the numbers have to match exactly. Now they're never going to match exactly, so this is never going to stop trying to iterate. If I do get into an infinite loop like that, I can hold down the control key and press C. That means Matlab, stop whatever you're doing and return control to me. I get the command window prompt back. As I mentioned previously, this looping structure here can be implemented with either a for or a while loop. We used a while loop before because the termination of the structure in our pseudocode was based on a relational operator. That can become part of the while loop structure, so we don't have to check that. So it's kind of natural to use a while loop for this. But it's perfectly okay to use a for loop. And in fact, there is an advantage. In a for loop, we don't have to explicitly update k. We had to have this statement in the while loop. For a for loop, we can update k as part of the structure. The penalty is that this relational operation that we have to check has to be done explicitly inside the loop, the way updating k had to be done in the while loop. So let's take a look at this using a for loop. Initializing these values can all be done the same as it was before, but we don't really need to initialize k because k is going to be part of the structure of the for loop. In our for statement, for will set k. Since term is initialized to 1, that corresponds to k equals 0. The next term we're going to calculate is going to be k equals 1. Now we have to decide where to end our loop. Let's make that variable and call this max iterations, maxit. Now I'm going to initialize maxit up here, and when I'm testing this code, I'm going to make that a small number. Let's just do 3 iterations. Inside the loop, this ports directly over. est is equal to est plus term. So the first time in here, term is 1, est becomes 1. We calculate the next term. Term is equal to minus 1 to the k over 2 times k plus 1. Now we need to check to see if this next term is going to be small enough to let us leave the loop. So if abs of term is less than EPS, we can break, which will exit this loop. We can end this, and then end the for loop. Here's the script file with my for loop implementation of the infinite sequence. I can run this from the command window by typing ex10p9, this is version B, and pressing enter. Starts at the same place. My first term is minus a third. My second term is 0.2. After that number of iterations, I get to 13 over 5. My next term is below 0.15 as far as an absolute value, so I stop iterating. It's working exactly the way that the previous program with the while loop worked. Now let's change a couple things around though. Let's make EPS 1e to the minus 5, and let's call this 1,000 iterations. Now if I'm doing 1,000 iterations, I don't want to see this calculation or this calculation, so I'll go ahead and save. Now if I run the program, let's see what we get for our estimate. Let's compare that to pi over 4. Well, it doesn't agree to within my 1 times 10 to the minus 5. So let's take a look at how many iterations we did. K is keeping track of the number of iterations. It got to 1,000 and then stopped. So it's not necessarily terminating as a result of this if statement if I get to the maximum number of iterations before this is satisfied. So let's see what happens if I do 10,000 iterations. Now I'm pretty much there, but let's see what k is. Okay, we still terminated as a result of the number of iterations rather than the result of the if statement. So with for loops, what you probably want to do is put in an error checking thing after everything's done to make sure that you haven't reached the maximum number of iterations before you stop. You need to make sure that you're actually terminating based on the tolerance that you're giving them and not artificially terminating because of the number of iterations. The plus side is that with a for loop, it's guaranteed to terminate. You won't end up in an infinite loop and have to terminate with a Control-C.